It is a great personal pleasure for me to be here again. I was here, when was it, 1994 when we did this the last time? Here? It's amazing. I'm not getting any older or anything, am I? Ha. Okay. Can you tell with this slide and the story we just heard from Jean that this is kind of going to be a tag team story here? Okay. So she didn't, you know what the phrase is when you steal someone's thunder? Well, she didn't steal too much, but maybe one slide. This is a very short presentation. I just want to let you know this. I feel it was very important for us, we at the University of Missouri, and when I say we, Mr. Chris Heim was sitting, we're about halfway back there on the left, and myself working on taking the resources that Jean began to introduce to you in terms of the plant material. And we are the ones who are actually going to try to phenotype and curate that plant material, okay? So that's where we're coming from. And I thought today's talk might be useful to those of us in the room who are interested in, yes, we know about the Quercus rubra genomic and genetic resources. We know about, it sounds, Quercus lobata is in the queue. And so, excuse me, and then so for us, Quercus rubra is where we fixate and focus our energies. So I'm going to run through this rather quickly. Christopher Heim, I mentioned, he's the graduate student in charge of the phenotyping. Myself, Arpita is in charge of the genetic mapping that Jean alluded to. Okay, so let's see. Here we go. So this is really straightforward here. Jean has already spoke to you about this. This is SM1. This is on the Purdue University campus. That's mom. And SM2, that's dad, okay? That's where we started from, okay? All right, and as she mentioned to you before, we, over the course of time, established seedlings now, open pollinated seedlings, which we identified were full sibs, okay? In two different geographic locations, one at Purdue University and one in extreme western Tennessee in near Memphis, okay, at what we call the University of Tennessee Ames Plantation, okay? So, what are we going to do with these trees? Well, first of all, the reality was that these trees were at Purdue, they were at Tennessee, Jean's in Notre Dame in Indiana, and I'm in Missouri, okay? So, it's kind of hard to phenotype in a timely fashion these trees when they're spread out all over the place. Okay, and they're also all different ages and stages, all right? So what we decided to do was to go to these plantations in Tennessee and at Purdue and basically repropagate them, just graft them. I've been doing that for a long time. It's a pretty straightforward thing with oaks. And so what we did was, over 2 different years, because Chris and I couldn't do all the work in 1 year because we have other stuff we have to do besides work on red oak, we grafted up a total of 409 northern red oak full sibs from both Tennessee and Indiana, and we established them in outplantings in Missouri for the purposes of phenotyping these trees. And boy, you know, and the end game here is to take this phenotypic data and try to relate it to the genetic map that Jean just talked to you about, okay? Because that's kind of what the objective is here. And as I said, in the lower left, this is the clonal population. So we have a little bit of power here because we have between 2 to 5 clonal replicates of every single full sib, okay? You have more power. Does it make sense? Okay? So the idea is to look at the phenotyping of this clonal population for QTL discovery. QTL, quantitative trait loci, okay, which we'll get to in a second. All right, so this is what they look like in 2013, summer 2013. And this is the work that Chris has been dedicated to in his program since he's been working with me, what, 3 years now? 3 years. So we have established a total of 387 graphs. You can read this for yourself. And in terms of the types of phenotyping data, what can you do on little bitty trees? Well, duh. You can look at bud burst, leafing date, you know, leaf marcescence and things like that, which I'll show you pictures of in a minute. So that's what they looked like in 2013. And then in 2014, I apologize straight away that in 2014, we produced about almost 900 grafted plants for 339 trees, full sibs. And I don't have good pictures for you of the 2014 outplanting sites. This is 1, 2. I'm not a very good artist. Can you tell? That little red squiggle up there, that's a kind of a long distance view of where we deployed those 2014 graphs. Okay, so this is where it gets a little bit hairy, at least for me, okay? So, as Gene alluded to, what we're going after here, we are looking at trying to identify regions along the genetic map that are related to phenotypic variation in the field using this structured full SIB population. Does that make sense? Okay? So these areas that we are looking for that provide, shall we say, signatures that related to our phenotypic variation that we're looking at in the field, they're called simply quantitative trait loci, or QTLs. Okay? That's the label. And what we try to do is to try to identify QTLs that are associated with stress resistance, long-term, adaptation, tree growth, development, okay, as the trees get older. For example, like flowering and fruiting, okay? Maybe we can begin to identify QTL regions associated with those early flowering and fruiting traits. Does that make sense? Okay? All right. And this is exceedingly important. We can't do this, we just can't do it without support. And the support that we received, as Gene alluded to, is from the Hardwood Genomics project, which I have the privilege to be a part of, as well as also Gene alluded to, the folks at INRA, led by Antoine and Catherine, in terms of their development of the Quercus rubra genomic resources, which we are, as Gene alluded to, taking advantage of. Okay? So this QTL stuff, let's, real quick. So this is my level of understanding. What Gene talked about, it goes like this, okay? All right? This is where I think I can understand some of it, okay? So the idea, you have, the objective is to locate these blocks of genes, these QTLs, that are associated with phenotypic traits. Let's look at, those two little red circles. Those are two full SIBs of this population we've been talking about. And one of them, the leaf looks like they had sinuses that are kind of not quite so deep. You can see there's two different leaf shapes there. Is that right? Yes? Okay. And so we can look at those different types of characteristics associated with those leaf shapes, and we can say, well, do those phenotypes, where do they differ? How do they differ in terms of their genetic or their genotypes, okay? The genotypic markers, okay? That's what we're trying to do. If we can find where how the phenotypes differ and how do they differ in terms of their genotype, that's what we're after. Okay, we're trying to put them together here. Okay, so again, INRA, Antoine, Catherine, what we tried to do in terms of the phenotyping of this plantation. We've already talked about establishment. Now, what are we going to do with it? Okay, we started with this online resource. Thank you very much, Antoine, for this. This is a wonderful resource. What we tried to do was to focus on QTL mapping of rubra using a series of traits that have already been defined and using the same definitions, okay, from the Quercus rubra database. We are focusing on currently, Chris is focusing on leaf morphometric data, leaf phenology, bud burst into spring, or early versus late, leaf marcescence, we'll talk about that in a second, and stomatal density, okay? So that's where we are. That's what we're doing right now, and that's right now, that's kind of enough, I think, okay? There are many more traits we could do, but we have, Chris is an army of one right now, okay? All right, so for leaf morphometrics, basically there are 1, 2, 3, 4 little red boxes on this table, table 1. It's from a certain person sitting about halfway down in the center of the audience. It's from one of his papers, and basically we use those types of approaches to look at variation in terms of leaf shape. Okay, that's something you can characterize and phenotype on very small trees. Okay, all right. So we have 4 different ratios that we are utilizing and trying to map based upon these definitions that were supplied by the folks at INRA. Furthermore, Gene mentioned this fellow who also is a friend of ours and a colleague, Oliver Gehling. This is from his work, who's sitting in the audience as well. We basically want to take these different leaf traits, and we want to try to take that variation in those leaf traits and associate it with markers on the map. Okay, that's what we're trying to do. So in terms of leafing phenology, I'm talking about leafing in the spring. Okay, again, we used INRA-based protocol with slight modifications due to the fact that Quercus rubra and Quercus rubra, they almost sound alike, but the leaves, they behave a little bit differently. So we scored leafing phenology over 2 different years, looking at this population, this full population. We looked at date of bud burst, which was indeed, this is, if I can do it, this is the most consistent, okay, characteristic we looked at in terms of the variation we have observed thus far. And this is what Chris has developed based upon the INRA-based characteristics, the definitions that they have used. So that's how we characterize bud burst over time for each tree over multiple years. And this thing about, marcescence. So as you can see, I think, this tree right there has this leaf retention in the dead of winter. This one does not. Okay, that's what we're talking about in terms of marcescence. This is where I think Chris and I would very much welcome your inputs, those of you who are interested in this. First of all, we know that SM1, remember those trees, mom and dad? Well, grandparents now. SM1 and SM2, they both are very different for this trait. We believe that winter leaf retention is under genetic control. And as a result, between mom and dad, we assume that the distribution of this trait among the progeny should be different, should be differential. Therefore, it should be an easy one, a good one to map. Make sense? Okay? So, it's easy to score. Pretty simple. Not a lot of error. That's another part about why I focus so much on the Quercus rubra track record and trying to use that to the extent possible in Quercus rubra. Okay? Because I want, if we have 190 pairs of eyes here, we want to all look at the same plant and come up with the same number on a given moment for a certain trait. We don't want error. It's hard enough to do this stuff, okay? All right, so, and we would welcome this from inputs from any of you folks, whenever, not now, but certainly maybe lunchtime. We don't have a really good understanding or a good reason. We've observed it, but we don't have a good reason for why it occurs or doesn't occur. What is it? Is it an what's the background story on this adaptation? Why is it an adaptive trait? This is the part I would welcome, truly. So one idea might be, does a lack of abscission layer development permit a leaf for the leaf photosynthesis period to extend longer into the fall season? Perhaps. So there's a theory again. In order to answer that, I'm sorry, I hate these things. We've been using a SPAD chlorophyll meter to infer leaf chlorophyll and also leaf nitrogen concentrations over time. And we're thinking that we can also potentially map SPAD readings over time for these different trees. And one thing that Chris and I have talked about, the lack of leaf senescence. Is it the inverse of bud burst? I mean, in other words, do it for a given tree. If it leaves early, okay, does it shed its leaves early? Or does it leaf late? Does it shed its leaves late? Okay, these are things we're looking at, okay? We have to quantify this trait, need to come up with a good way to do that. Currently, what Chris is doing, like when we leave early tomorrow morning to get back to do more of this data collection tomorrow afternoon, he's looking at 3 different leaves per ramet, looking at them every week throughout this time of year. He wants to see how long the season goes, okay? How long the growing season goes. All right, one last thing, and I'm almost done. Stomatal density. Other speakers yesterday spoke about this trait, this characteristic. And we first, I'm sure I said, it's the royal we. Chris first, okay, started out looking at stomatal conductives, SC, okay, in the populations of trees we're working with. However, conductance for us, for our situation, it didn't work well. because there's a lot of microsite variation, one field versus another. Same clone is planted here and here and here. But the variation was it was a little squirrely. How about that? Okay? And there's also variability for stomatoconductance among flushes within one single tree at a given point in time. Okay? So Chris told me that stomatal density, however, seems to be much more stable and much more consistent. Okay? So we're going to go with that at this point in time. And as we say here, stomatal density is a factor that's associated with gas exchange and limiting water loss. It could be used as a proxy, or it has been used as a proxy for water use efficiency by others. Okay? All right. So over time, as the trees get older, I want to also look at these trees because they're only this tall. However, remember they come from the 2001 seed year. Remember that Gene alluded to? So they are the age that they are, even though they're only in the field 2 years old. Does that make sense? Okay. So we should have a potential very soon now. I thought it was going to be this year, honestly, but it didn't happen. Next year, we're hoping. We can begin to document the timing and the precocity, if you will, of when the pistillate and staminate blooms arise on these trees over time. And again, try to put them on a map. Okay? All right, let's see. I think this is the last slide I have. And remember we talked about SM1 and SM2 are now grandma and grandpa. Okay? These are the trees. And so there's family 1, family 2, family 3. And we are in the process as we speak. Gene alluded to this person called Arpita. She's wonderful. She works as a graduate student in her laboratory at Notre Dame, and she is in the process of defining who are the full sibs within each of these 1, 2, 3 open pollinated families. So we hope we will generate enough F2, truly F2 full sibs. Okay, so we'll have the parents, we'll have the F1s, and we'll have the F2s. So that's where we stand at this point in time, and I know we're running a little late, so I want to probably shut it off right there. One last thing, however, that huge acknowledgement slide that Jean put up, she and I talked about these, both presentations yesterday afternoon. I said, well, yeah, Jean, I really got to put an acknowledgement slide together because I hadn't had the chance to do it. And I saw hers. Everything that was on hers, same for me. Okay? So I'm all done. Thank you very much.